So your boss sets you a task. Find the best possible location for our next physical store.
You're a data scientist,
they say.
so you should be able to get to the right answer quickly.
Let's pretend this is a perfect fantasy and you have the data you need, the locations your ideal customers spend most time in, prioritised by the biggest spenders. So you come back. We should launch a shop in Battersea. Your boss nods and goes,
Great, where in Battersea?
and that's where you're stuck. You know Battersea is where all the cool kids hang out, but that's not the same as knowing which available commercial lots are in high footfall areas that said cool kids frequent. If your boss wanted to get the answer Battersea, they probably would have Googled around and come up with a similar conclusion. But from a data scientist, they want specificity. To answer this question, you need to learn about a lesser known area of data science. Welcome to Geospatial Data Science. My first foray into geospatial data science was when I was trying to understand how oil moved around the world for European Scope 3 regulation. For those of you not up to date with the latest European sustainability initiatives, Scope 3 is a reporting standard that looks to capture the indirect emission footprints of companies. So it's not the emissions that the companies themselves generate, but the emissions of their supply chains or their employees commuting to work. A deep dive into Scope 3 reporting is outside of the scope of this video, but I wanted to use it to show how spatial data science can slip into a normal data science role. Because in order to calculate the emissions of your supply chain, you need to understand the carbon footprint of all of its component parts, including how things are shipped around the world. But just because you know the plastic in your oil came from a US refinery that mostly refines Saudi Arabian oil, doesn't really give you any information about the carbon impact of how that oil got here. That's where spatial data science comes in. Because spatial data science is, at its most fundamental, data science with locations attached. It's the ability to restrict all areas where your ideal clients live down to just the ones that have lots with commercial zoning. It's the ability to manage the optimal distribution of water in a drought. And it's the ability to calculate the carbon costs incurred shipping oil around the world according to the routes the ships actually take, not just as the crow flies. So in this video series, we're going to break down some of the most important fundamentals of spatial data science from the perspective of a data scientist tasked with solving geospatial problems. That means that I might not be giving you the perfect method or optimal theory for solving all of your geospatial problems. So if you're an expert on this topic already, I'm not going to take umbrage with you sharing your tips in the comments below. But what this does mean is that if you're a data scientist new to the world of geospatial data, I will be giving you the tools you need to get off the starting block. And if you stick around until the end of this video, I'll even suggest a little project you can get stuck into to apply some of this stuff as well. So let's kick it off with a very fundamental question. What even is geospatial data anyway? So geospatial data is any kind of data that has a concept of space or location baked in. For example, this could be the latitude and longitude of the capital cities in the world. It could be locations of supermarkets in London. It could even be the world map of your favourite Pokemon game. And no, I will not be accepting critiques of my Pokemon gaming choices. The important thing to note is that there are two key concepts here: where things are and how far away they are from each other. Where things are is a simple enough concept. It's where X marks a spot, the address or location at which the thing is. There are a number of ways in which we can refer to the location of something, but if I asked you how close 20 Fenchurch Street is to 10 Downing Street, unless you know London fairly well, those two addresses give you absolutely no concept of how to actually answer that question. That's why most locations for data science are given using a latitude and longitude coordinate system, where latitude runs between -90 and 90, south to north pole, and longitude runs from 0 to 360. That doesn't have to be the only method of identifying coordinates. Mathematicians have spent significant time playing with different coordinate systems, and there are a variety already established just for mapping the Earth, but let's be real. Most of the data science you're going to end up doing is going to end up using lat-long coordinates or something similar, so the discussion of different coordinate systems is well outside of the scope of this video. A lat-long pairing, however, is incomplete information. In the example of capital cities I gave earlier, the lat-long often just describes the centre, but tells us nothing about where the city starts and ends. Is Staten Island a part of New York City? Who knows? The lat-long centre doesn't tell us. You might give me the exact lat-long coordinates of the bookshop in the shopping centre, but that doesn't tell me what floor it's on. In a similar vein, the concept of how far away things are from each other has its own intricacies as well. If you're asking me how far London is from Sydney, you're not asking me to stick a ruler through the centre of the Earth and tell you. You're more likely to be asking for the distance travelled over the Earth's surface, or maybe you're actually asking for time. 17,000 kilometres might not be something that's meaningful to you, but 24 hours in a plane is. But London to Sydney in all of those configurations is always a somewhat straight line, ignoring the detour for the layover. In reality, if you're asking how far away your friend's house is, it doesn't matter if it's just 2 miles, if it requires weaving around complicated country roads, or changing tube lines twice. The concept of distance is variable according to the use case you're using. And if there's one thing I want you to get from this video or the EvilWorks YouTube channel in general, it's this. Before you can even start to do the data science, you need to understand the actual problem you're trying to solve. Not the maths you're going to use, not even the data set you need to tidy up. Your first step is understanding the fundamental business or life problem that comes your way. Only then can you make a decision about the maths and the data that you use. So with this in mind, let's look at my problem from earlier. How do I calculate the carbon cost of transporting the oil used in my plastic? In order to answer this question, I need those two things, location and distance. So let's talk about what this would look like. So if I start by thinking about location, in order to calculate my shipping costs, I need to understand how oil gets from A to B. So I need to decide what that A and B are. Now, the reality of oil shipped around the world is that it likely gets extracted and then goes into pipelines or into trucks. For the purposes of this exercise, we're going to look at emissions only from the literal shipping. That's oil on tankers moving across the sea, so we'll make the assumption that the pipeline or trucks take the oil to a port where it's loaded onto a tanker to set sail around the world. On the other end, the reverse likely happens. The oil is taken from a tanker and loaded into a pipeline or onto a truck and taken directly to the refinery. The oil started at point A, where it was extracted, and ended at point B, the refinery. But just as I emphasised, the only part we care about for this part of the calculation is the shipping. So really, our A is the port from which the oil tanker leaves, and B is the port of its destination. It's at this point in which I make my first domain knowledge informed decision. Shipping ports are often pretty big, especially ones that take in a large volume of oil. As a result, you could well argue that I'm in a situation where a lat-long pair for the centre of the port isn't going to cut it. I'm going to need an exact location of where in the port the oil will be deposited. But data science is an optimization problem in many ways. I could go looking for that information, build an entire data set with the exact locations within ports that oil tankers deliver. It doesn't exist, I already tried. And deliver the project 6 months late. Or I could realize that the distance within a port is tiny compared to the distance these ships have traveled across the world. And in this particular use case, the center point of the port is probably good enough for a reasonable approximation for this project. So I grab the general lat-longs of the port and call it a day. Location problem solved. Where the real fun comes though is from working out the distance, and this is where the project of this video comes in. It's a small one to kick you off, but don't worry, we'll be doing more advanced stuff as we delve deeper into the world of spatial data science. So the challenge is, how do we calculate distance from our extraction port to our refinement port? I'm going to give you 4 ideas for how to do it, but if you can think of more, then go for it and let us know in the comments. So the first is simple, our basic as the crow flies distance. If you put your finger on the map of the world at Yanbu Port, the largest oil port in Saudi Arabia, and draw a straight line to the port of Houston, one of, if not the largest oil port in the US, what distance do you get? For those of you who know your geometry, you've probably worked out it's the Euclidean distance without needing to calculate it. And if the distance between the 2 ports was small, say within the same town, this might be a reasonable approximation of what the distance actually is. But we're talking about shipping oil around half the world, and while the horizon may look flat from your doorstep, the reality is that Earth has a curvature, and this needs to be taken into account in our calculation. Your next challenge then is to calculate the Haversine distance, the distance between 2 points on the Great Circle Sphere. This one requires some trigonometry, or you can just use the sklearn Haversine distances implementation. Depends how deep you want to go. I'll leave that one up to you. This is better because it's far more accurate to the actual distance between Yanbu and Houston. But as you probably noticed by now, we've got a bit of a problem, and that's the fact that an oil tanker can't plough straight through Egypt. We'll do a more detailed video on how to create actual routes for data science, and spoiler, I did something similar for a Halloween video optimizing Bart's trick-or-treating route around Springfield, which you can find linked above, but we'll cover it in more detail in a follow-up. But for now, a way you might overcome this is to plot a route. A path leading from Yanbu up through the Suez Canal, through the Mediterranean, the Strait of Gibraltar, and across the Atlantic Ocean. One way to do this is piecewise, breaking down the route into as many checkpoints as you need to stay in the ocean and calculating the distance between them all, adding them up to get your final result. And the last challenge requires a bit of domain knowledge, which is why I harp on so much about understanding your business problem. I know, because I've done the research, that oil tankers from Saudi Arabia to the US don't go through the Suez Canal. It's such a tight choke point that ships are vying for the opportunity to pass through, and where demand is high and supply is low, that's where the money-making opportunity is. Passing through the Suez Canal is very expensive, so oil tankers to the US just don't. They actually go around the Cape of Africa before making their way back north to the States. So your challenge, should you choose to accept it, is to calculate the distance of an oil tanker travelling to the US via all 4 methodologies. Let us know in the comments how you got on and what challenges you came across. We're not done with distance for now, as there are a number of interesting things I could say about it, and we also have to dive deep into when lat-long centre points just won't cut it for locations either. So subscribe so you don't miss both those videos on spatial data science.